welcome to Breakout Nils edition. This is our recreation of the classic Atari Breakout game using the FRDM KL46Z microcontroller as the game controller. So for our capacitive slider control, the capacitive touch slider on our board acts as the primary input for the game. When you slide the finger across it, the board's touch sensor module reads the capacitance values. These values are processed by the get slider position function, which calculates a position value between 0 and 100 based on the relative strengths of the left and right electrodes. This position data is then sent over UART to the computer, where the Python game converts it to a percentage and positions the paddle accordingly on screen. The SW1 button on our board serves as the pause button. The SW3 acts as our reset button, so you can press this to start a new game. If the game's over, you'll need to reset from the computer since the serial communication loop in Python pauses during the game over state. Each time the ball passes the paddle, a life is lost. You start with 3 lives. Notice that the red LED on the board flashes every time you lose a life, which provides visual feedback. And when all 3 lives are lost, it's game over. And each time all the blocks are cleared from the screen, you advance to the next level. Each level adds an additional row of blocks and slightly increases the speed to increase the difficulty. And after you beat all the levels, you win.
Here's a close-up of our microcontroller board in action. As you can see, the LCD display shows the current score in real time. There's a small delay in when the score updates to preserve smooth slider functionality. The score is sent from the Python game to the board through serial communication, which is parsed through the score prefix and then displayed on the LCD. Notice the red LED flashing whenever a life is lost. This visual feedback helps the player know they've missed the ball, even if they missed the life lost on the screen. The system architecture consists of 2 main components. First, the microcontroller code, and second, the Python game engine. For the microcontroller for core functions, touch-init configures the TSI module for the capacitive slider, and then get slider position processes the raw electrode readings to determine the paddle position. Then our main loop transmits this position data to the Python game while also checking for incoming score updates. The LCD then uses the score it received from the Python game and uses basic division by tens place to convert the score into a single number for each tens place to be displayed. Finally, we've implemented interrupt handlers for the buttons that set flags, which are then read in the main loop.
We're using Pygame for graphics and PySerial for communication with the microcontroller. The Python code implements a proper game loop with physics, collision detection, and rendering. A separate thread handles serial communication with the board, reading control inputs and sending score updates. Finally, we call the read serial function, where it looks at the UART data and parses. It takes in the slider and button data and uses that to set the game state accordingly. One major issue we encountered was interference between interrupts and the touch slider functionality. We solved this by implementing critical sections with interrupt disabling. We also had to carefully balance the update frequencies, since too many LCD updates would monopolize the serial port, causing laggy paddle movement. Debugging the touch slider calibration was also tricky. What we did was we ended up implementing a baseline calibration at startup and applying thresholds to filter out noise. Finally, serial communication timing was also another big challenge. We had to implement proper buffering and check that the UART transmit register was empty before sending new data in order to solve this challenge. Overall, this project gave us practical experience with real-time systems, hardware-software interfaces, and bidirectional communication protocols.